So then I'll start with mode locking. That mode locking is the common name, but it really means mode synchronization. So all the modes that I have showed in the previous slide, which is like this, all the modes out here, we want to lock all of them. We want to synchronize all of them so that they have a a phase relationship between all of them. So if you have a phase relationship between all of them, then all of them can laze and extract from this gain medium. So we have, how do I do this? So how can I synchronize all the modes? So let me start with few baby steps. Out of all these modes, let me take only two. Let's consider only two, and let's see what exactly happens to this two. And then we will extrapolate it to all the modes that are possible. So here consider these two frequencies. There are two modes, two very closely related frequencies. They may be one next to each other, the modes. So the frequencies are apart by just that delta nu. Okay. So here I show in black, you can follow the black line, that is one wave. So in order to, and then this is the red line, which is another frequency. So as you know, light has this dual personality. It can be a particle, can be described as a particle matter, or it can be described with a wave character. So in this derivation, I am making use of the wave character of light, okay, in order to come to some conclusions regarding mode locking and mode synchronization. So if you just pay attention a little bit here to these two frequencies, the red and the black, you can see in this region they are destructively interfering, not exactly in phase. Zero phase difference is not there between the two. While here in this region, see, you can't see the black, you can only see the red. The black is just behind the red, and they are perfectly synchronized. Okay, they're sitting one on top of the other. Again, you come to a region where they are not synchronized well at all, and they are interfering destructively. Here again, you have a region where they are interfering constructively. Okay. So what is the outcome of all this? Suppose you superpose these two frequencies, say with omega 1 and omega 2 frequencies. There are two monochromatic waves with these frequencies. Assume that the amplitude is the same for both of them, okay, and the amplitude is E0. Okay. So the outcome of this is in the same picture. The outcome of this is a wave which looks like this. These are called beat waves. You may have heard about beat waves. It comes in sound also. You get beats, a regular beat at a regular interval of time. So you'll get sounds which are at regular interval of time. Okay, this happens when two close sound frequencies overlap with each other, and you get this sort of a character. And the same thing happens even in light. Both of them are treated as waves, and the conclusion is really the same for both. So when I have two modes overlapping with each other, I'll get something like this, which are called beat frequencies. Okay. This is actually, when I show this, it is the actual light part. That means I've taken the E star E, or it's the intensity basically. Here I'm considering the wave or the electric field associated with the light. Okay. So here it is a wave, and a wave is described as E0 cos omega 1 t minus k1z. z is the direction of the wave propagation, and E2 is E0 cos omega t minus k to z. Here again z is the direction of wave propagation. That means both the waves are propagating, say suppose this is the z direction, it is all, both of them are propagating that way. Now when I by the superposition principle, E, the final wave, is equal to E1 plus E2. Okay. So I put E is equal to E0 cos omega 1 t minus k1 z plus E0. I add this and these two I have just placed here. Okay. Now in the next step I use a identity, a mathematical identity, okay, which is the sum product identity, which is given as follows. Cos A plus cos B equal to 2 cos A plus B by 2 into cos A minus B by 2. Okay, so that is the identity that I will use. Okay, and if I use that, so I come to this conclusion. So cos multiplied by cos, and you have all these things inside. Okay. Now just do a little bit of algebraic jugglery. K1 is equal to omega 1 by c, K2 is equal to omega 2 by c, the wave vector, and so it comes out to be, I just rearrange the terms here to make it easy for us to interpret the kind of wave that is the final wave. Okay. So here it is omega 1 minus omega 2 into t minus z by c divided by 2. Okay, and cos of omega 1 plus omega 2 t minus z by c by 2. Okay. So I have this term t minus z by c by 2, t minus z by c. This shows that the wave is travelling in the z direction with a speed c, okay, in time. Okay, so this here is the time axis, this is the time axis. So it is moving this way. Okay. And I started off with frequencies omega 1 and omega 2, and I come and I land up with two more frequencies, omega 1 plus omega 2 and omega 1 minus omega 2. So obviously omega 1 plus omega 2 is a larger frequency, is a bigger frequency, and this is a kind of a slower, obviously it is negative, minus omega 1 minus omega 2, so a slower frequency. So what does this equation mean physically? Okay, one, that this whole thing is travelling along this z direction, and the next is omega 1 plus omega 2. So this frequency here, which is moving faster, 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 which is a bigger frequency, corresponds to this term, and the slower frequency corresponds to this, the dashed line. Okay. So I have these faster frequencies which are there, which are clubbed together, and this is a slow frequency. Okay. So this is the beat frequency. So that is the interpretation of my superposition of two very closely spaced frequencies or wavelength. So my ultimate outcome is a set of beats like this. Okay. Set of beats, in case of light I will not call them beats, they are pulses, pulses of light here, and they are separated out in frequency like this. Though this may not have been the separation between omega 1 and omega 2. This separation, the beat frequency, is completely different. Okay. And even this is like a wave packet, you know, and you take the E star E square, which gives you the intensity. So these are pulses. This is the intensity, okay, of these pulses. So this is what I get when two modes are lasing in my medium. Okay. But my aim till now was not to just make two modes synchronized and lasing, but my aim is to get all the modes within the gain profile to be synchronized in such a way that all of them are able to extract gain from the medium, all of them are able to lase together in order to get the maximum extraction. Okay. And a side effect of this mode synchronization is pulse shortening. So, you get a very short pulse. It can be called ultra short. Okay. That is a consequence of mode locking. So, I started off with two modes. Now, let me take all the modes. Let us assume that all the modes are synchronized. Okay, so, I start off here. So, in the picture I have shown 1, 2, 3, 4, 5 modes which combine together, which will be superimposed, and they give you this sort of a wave structure at the end of it. Let us put it in exact mathematical terms to understand this structure better. Okay. So, now I start off say with, so again there will be a superposition of waves with equidistant frequencies. All these frequencies are equidistant in the frequency scale. Okay. So, let the equidistant, so suppose I superpose all of them, E t, the final one, will be E 0. Remember, E 0 was the amplitude of all of them have the same amplitude. Cos omega t, omega is the first frequency, okay, this frequency may be for this. Then you have E 0 cos omega plus delta omega is the frequency separation. It is somewhat similar to delta nu, I have just put it as a delta omega. Quite often it is used as omega, nu or omega, but again this is the frequency spacing as I have said in the previous slide. So, delta omega, so this frequency is omega plus delta omega, this one. So, you have cos of this plus another wave is superposed, that is E 0 cos omega plus 2 delta omega. So, I am looking at this frequency which is higher than this and this, as you can see, because delta omega is getting added each time. So, this is another wave which I have put down here. Then there can be a third wave which will be omega plus 3 delta omega t, which will be this. Next one will be 4 delta omega t, and so it will go on and on until you have n such frequencies, which will be omega plus n minus 1 delta omega t. So, here I have added all these waves. It is a superposition, so there is an addition exactly like in the two mode case. Okay. So, it is really a long right hand side. So, let me write it in a shorter form. Shorter form would be to represent it in an exponential representation. So, any wave, you know, cos can be written or any wave can be written in terms of an exponential term, e to the power I omega t plus n delta omega. N is the number of modes which varies from 0 to n minus 1. Okay. So, this is my superposed wave put in a short form. This is the same as this, but put in a exponential form, which looks shorter and neater. And of this wave, this is my resultant wave by addition of all these waves, and I take the real part, RE is the real part. So, because there is a I factor here, so I need to mention that I am taking the real part. So, from here I can see that E t E 0 can be written as real of e to the power I omega t. I have just taken out e to the power I omega t from here outside the summation, because the summation is only over n. So, n is equal to 0 to n minus 1 e to the power I n delta omega t. Now, I use the summation of exponential mathematical identity. Okay. Now, this is I have to take the summation. What does the summation come out to be? That is a mathematical identity also, and that is equal to E0 e to the power I omega t, which I already have here, and this summation part works out to be this part 1 minus e to the power I n delta omega t, capital N, 1 minus e to the power I delta omega t. Okay. This is a mathematical identity which you can look up in any mathematical physical mathematics books or anything. Then so this goes out to work out to something like that. Here nothing has been done, just a little bit of jugglery of e to the power I n delta omega t, just so that we get into a form that we can interpret, the final form of the wave can be interpreted well. So, this is some algebraic stuff that I have done here, and this were you have to look into it carefully. I have taken out common e to the power I n delta omega t by 2. So, here also I get divide by 2 the exponentials, and so this is my final form of this wave equation. Okay. Now, this part, if you see, consider just the sign part here, this part is here, and this part, okay, I have written it in terms of cos. I started off with cos, taken into an exponential form, and I write back again into a cos form. Okay. So, I have put it as cos of omega t. Now, this omega within the brackets is the average frequency. Okay. So, this is my final form of equation, just have a look at it. It has a sine term on top, it has a sine term below and a cos term here. Okay. So, omega is the average frequency. Let me just jump to the next slide where I have just written down what here. Delta omega. These are some approximations used in the last part of the formula there. So, delta omega is omega plus n minus 1, that means the total number of modes, and into delta omega, which is the frequency separation, divide by 2. So, this gives you, this has been put into bracket to show that this is kind of the average frequency. The frequency is increasing with every this, but this gives you an average. So, omega within this bracket is the average frequency. Okay, I will just toggle between these two slides. So, here I have put it here as delta omega. Now, just look at this part of the function. Okay, here I have just again, if you see, I have if you see inside the bracket, a little bit of manipulation is done. What manipulation? Again, going back here. So, it is easy to recognize that n into delta omega will be this bandwidth. This is the total number of modes, separation between two modes. Obviously, this will be the total width of the frequencies of the wave packet. Okay, this will be the total width. Okay. So, for most practical purposes, n is much greater than 1. N goes into hundreds and such odd 100, 200, 300, those kind of numbers. Okay. So, it is much greater than 1. So, the argument of sine in the denominator, that means sine of delta omega t by 2n, which was there in the denominator, can be written almost as delta omega t by 2n. That means sine x, x is a very small sine x is almost equal to x when x is small. Okay. When x is small, sine x is so. So, that is how I get my this identity. Okay, going back again to the previous slide, so you know where it is. So, this is what I have done here. this is exactly this, okay, here 2n, and I have made that approximation that sine this part n is so large. So, this part in this argument becomes very small. So, that is how I have made that approximation, that turns out to be delta omega t by 2. So, this function looks like sin x by x, okay, sin x by x, and this is cos average omega into t. So, what does sin x by x look like? So, sin x by x actually it is something like this, okay, this part. So, basically it is, you look at this function, all these small oscillations here, the peak over there and then it is coming down and all that within this envelope, that is all sin x by x. Okay. And if you were to take, if you wanted the intensity will be equal to E star E, which will give you the intensity, which will be on this side. There will be nothing on their negative side. Okay, but I am dealing with just the wave part, not the intensity part. So, that is how you get this wave. So, this part within here, this tall part corresponds to this, and this cos omega t corresponds to this red line, which is a slow kind of a frequency moving along the z axis. Again, this is along the z axis. So, you have the sine part which is here, and here you have the cos part which is moving along slowly. So, what you actually have in the intensity profile, intensity again if you have taken the square, and what you will actually see out is pulses of this intensity. So, you will get like this, and it will go on and on. This is intensity, okay, and this is time. Okay, so here is that wave function. So, this part is the slow cos part, and this part is the sin x by x part. Okay. So, again you get these pulses, something like those beats. So, here in those beats only 2 of them were able to superimpose and have a constructive interference, and here I have another pulse. Again, all these modes are superimposed and are able to have this constructive interference. Okay, this page is actually, I have just given what I could not write in the other slide. See, the wave packet is a pulse like this. The maximum amplitude is observed at t equal to 0, where the oscillations are added in same phase. Okay, so I will toggle back. Here you get the maximum, where all of them, all the waves are in phase. This may be slightly little out of phase, but then the center one is all in phase. This happens at t equal to 0, at time equal to 0, okay, at exactly that center time and time equal to 0. That is what I have just written here. When t equal to 0, where the oscillations are added in same phase. Mathematically, it is a singularity. Okay. So, basically sin t by t is at t equal to 0, t is equal to 0, tends to 1. It is a singularity. Okay. So, if I go back, so this is a singularity here. Okay. So, now I must so here, so what must I do? Now, what I want to say is t is equal to 0. Now, the next 0 amplitude, when does it become 0 again? will be at t equal to pi, okay, because sin pi is 0. Okay. So, sin pi will be 0. So, the whole thing will become 0, okay, that whole sine part of the function. So, delta omega t divided by 2 will be equal to pi, this one delta omega t divided by 2 will be equal to pi. Okay. So, if I go back to the here, this last part, delta omega t by 2, delta omega t by 2. This delta is not the small delta, this is the big delta. Okay. That will become 2. So, that will become pi. So, delta omega delta t, in place of t I have written delta t divided by 2 becomes pi. So, nu, here I have just brought in that nu part, nu is equal to, where nu and omega are almost treated as equivalent, nu is equal to omega by 2 pi. So, delta nu delta t is equal to 1, if you just substitute here, this is just a jugglery of this delta, but this is a very important formula. Delta nu delta t is almost equal to 1. The modes will interfere constructively at times t is equal to 2 d by c. That means the round trip time, they will all act constructively. Okay. So, delta nu delta t, you know, there is this gives a kind of a fuzziness to the frequency and time. Okay. So, if there is a fuzziness in the measurement of delta nu, then delta t may be exact. If there is a fuzziness in delta t, then delta nu will be will not be so exact. So, it is something like the uncertainty principle. Okay. It is the time bandwidth product. It is a very famous product, time bandwidth, okay, because this is the time and this is the bandwidth. Time bandwidth product is equal to 1, something like the uncertainty principle. Okay. So, I will carry on in the next lecture on mode locking, specific mode locking, and I will give examples of them.